Hello, everybody. Good morning. This is the Thursday morning, the last day of VMV 2020. And usually this is the worst slot for a scientific presentation you can pick, because usually this is the day after the social event, early morning, everybody is asleep and it's a really hard time. This conference, things are different. As you know, there was no social event yesterday. So that means everybody now is awake and motivated for listening to the presentations. We have two interesting presentations in this session and one invited talk. We start with the first paper. The authors are Quynh and Lars Linsen from University of Münster. And the title is Interactive Generation of 1D Embeddings from 2D Multidimensional Data Projection. Let's get started.
Thank you, Holger, for the introduction. I hope that you can see my screen right now. So yeah, good morning, everybody. Welcome to my talk, Interactive Generation of 1D Embeddings from 2D Multi-Dimensional Data Projections. So please let me begin with a brief introduction about high-dimensional reduction techniques and related pattern recognition tasks. In many application scenarios, it's necessary to understand the distribution structures of a subset of elements, and this subset might be in a high-dimensional space or an abstract space where similarities among elements can be derived here. And then common practice to tackle the task is to apply dimension reduction techniques such as MDS to preserve the distance, or TSNE to preserve the neighborhood, or recently we have UMAP. And then by observing the plot in the 2Ds, we can see whether the data set have clusters or outliers, something like that. And in many scenarios, using dimension reduction to 1D can provide one extra axis for another interesting visual encoding. For example, we use like here, the y-axis stand for the 1D projection, and here we use the extra axis to test if different labeling strategies are suitable with the similarity pattern in the static view, as we did in a work that were published in last year VMV. Or another scenarios of applications of 1D embedding is to provide a static timeline for time varying data with the extra axis stand for time. So those application scenarios motivate us to study more about 1D embedding. We all know that there is a variety of dimension reductions techniques. Working with these reduction techniques, we observe that despite the good performance in generating 2D embeddings, the 1D embeddings often exhibits a much lower qualities for pattern recognition tasks, which is most likely due to the low degree of freedom. For neighborhood preservations, TSNE is a popular dimension reductions techniques to use. In these particular examples, we see in the left image here, the 2D TSNE embeddings output good results where clusters are well separated. In the same time, the 1D TSNE doesn't give us that good result. For example, here, the red cluster got separated. And we would like to test if the difference is statistically significant, as the outcome of the embedding depends on the initial random configuration or some hyperparameters such as perplexities or number of iterations. So we compute an ensemble of embeddings and perform a quantitative measure for the ensembles in form of a box plots. And the outcomes of the quantitative quality assessment is that the 2D TSNE drastically better, and the 2D TSNE is already perfect in compare with the 1D right from the 10K step. And let's go for another number of iterations, like 290K steps. And this provides us the evidence that automatic generated 1D embeddings can be worse. So we propose to overcome the issues by involving the users. So there are multiple arguments for our strategy to be useful and successful. Firstly, interactive in 2D is very intuitive for humans, and they may outperform automatic solutions. Secondly, interactively defining a 1D embeddings in a 2D space is very simple, when users just need to draw a curve that fits the data on the 2D projections. And thirdly, the users can define a mapping according to the analysis tasks in mind, and they can bring their own experiences and expertise in pattern recognition tasks. And finally, often the designed embeddings have primary or secondary design goals where the weighting is hard to determine automatically, while the user is able to find the best trade-off. So the main idea is to create, I hope that you can see. So the main idea is to create an automatic mapping to a 2D embeddings, and then let the user define the last step of mapping from 2D to 1D embeddings. Then user can draw a piecewise linear curve on top of the 2D embeddings. Then the 2D points are projected onto the curve to have a 1D embedding. As we can see here is that our interactive 1D seem to preserve structures better than the 1D Disney. And we perform a user study to evaluate the robustness of our approach and quantitatively compare the quality of our approach 1D embeddings to 1D and 2D embeddings obtained by Disney. We see here an example of generated curves from user for a data set. They show the variabilities and strategies of users in drawing the curve. We ask users to perform the study for 4 more data sets beside the 4 cluster data sets, the Flame data set, the R15 data set, and the aggregation data set. So in order to test the different performances among the methods, we use the quantitative measures as we used to compare the 1D and 2D Disney before. So to validate the cluster preservation qualities of the embeddings, we look into the silhouette coefficients of on points in the embeddings. This coefficient measures how well it is for a point belong to each class. For instance, this point have positive silhouette coefficient, but this point is so far away from each class, so it has negative silhouette coefficients. And the qualities can be quantified by a volumes in the range between -1 and 1, where larger the values are better. And in particular, we propose to define an outlier index as the percentage of the positive elements in the embeddings. And this index is always in the range between 0 and 1. The higher the values, the better. We compare the performances of the 1D embeddings with preserving cluster using the outlier index. Using these measures, the performance of our methods is already comparable with the 2D Disney and outperform the 1D Disney in this data set, this 4 cluster. And it is similar to another data set. So we can conclude that in general, our methods actually outperform 1D Disney. Having said that, please let me move on in the second part of my talk. As we mentioned in the beginning, one of the main motivations in introducing 1D embeddings were to show the temporal evolution of time-varying multi-dimensional data in an intuitive visual encoding. First, we tried dynamic Disney, a technique that takes an ensemble of similarities matrix as inputs and claim to output coherence embeddings among time steps. In particular, we observed the timeline of dynamic 1D Disney here for a data set that includes 4 clusters. The colors of the lines are used to encode for class of the clusters. So in the range of the observed time, the 4 clusters don't merge in the original data. However, the timeline from dynamic 1D Disney, as we see here, some shows some merging like here some time step like here, here, something. And the cluster are switching location to each other, as we can see here. So the challenge now is to have a 1D embedding timeline that is more faithful with the original data. So we extend our work to tackle the problem. So we deploy dynamic 2D Disney to provide the 2D projections for every time steps. At the first glance, we only draw the curve on 2D projection of the first time step and fit it to the following time steps. Our initialization produced a much more stable result. But after many time steps, the timelines of the clusters starts to cross each other, as you can see here. So we observe that actually the dynamic 2D Disney is not so robust enough and introduce the rotation of cluster pairs and cause the problem. So to compensate the motions that the dynamic 2D Disney introduced, we propose to use an automatic checking of the curve, 1D curves that were drawn by the user in the first time steps. So for each controlling points of the curve like here, we keep track of its location, local coordinates according to a PCA systems. And using these techniques, we can see the mixings and the splitting event of those cluster in the timelines in a static view like the timelines. And we can check back the 2D projections with the tracking curve at the selected time step like this. And compare with dynamics to 1D Disney, when we use a lot of time step like this, the dynamics 1D Disney looks very messy. And our techniques show a better result. So even though our approach is promising, the rotations of cluster pairs introduced by dynamic Disney is one issue. These rotations cause the cell intersection of the checking curve that result very bad artifact in the 1D embedding. We acknowledge the issues and would consider it for future work for checking the curve in 3D instead of 2D space, or develop a dynamic 2D projection that does not introduce such rotation artifacts. And one of the current solutions is to allow user to redraw a curve at any selected time steps. And we show here a video showing the checking curve. You can see in the left side is the 2D and the checking curve accordingly. And then in the right side is the timeline, the 1D timelines using our approach. And we can see in the animation that 2D dynamic Disney introduced quite often the rotation of cluster pairs. However, our timeline still reviews the mixing and the splitting events quite good. For instance, here we see the mixing phase start to emerge in the timeline. And then later on, we using this timeline, we see that, okay, those clusters, they're gonna get separated soon in the splitting event. For instance, they start to split now. Yeah. So putting it all together, we have presented our main contribution that includes firstly, quantitative comparisons between 1D and 2D Disney for cluster preservations. Secondly, a semi-automatic approach to generate 1D embeddings, where a 2D embeddings is generated automatically, and an user-centric approach is proposed to perform the 2D to 1D embeddings. A user study to evaluate the robustness of the user-centric components to our approach, and a quantitative comparisons of the quality of the 1D embeddings achieved with our approach when compared with 1D Disney, and an attention to embeddings for time-varying multi-dimensional data with an automatic adjustment of 2D to 1D mapping. So in summary, we can conclude that our interactive 1D embeddings approach produced desirable result. And we showed that our approach can be coupled with a dynamic Disney approach for time varying multi-dimensional data. However, the goals of the examples was neighborhood preservation. Consequently, desirable properties of projections such as preserving distances are not fulfilled. Another issue is the cell intersection of the curve that is caused by locally rotation of some clusters. And for the future work, we would like to test if tracking the curve in a 3D space can remedy the issues. And in case of different design goals, for example, if such a design goal is defined priorities, we would like to consider automatic approaches to find suitable curves. So thank you, and I'm happy to answer the questions now. And anyway, by the way, I'm looking for a postdoc position. Thank you.
Okay, thank you, Quynh, for this very nice presentations. We have time for a few questions. So if you have questions, please step up to the microphone, state your name and affiliation, ask the question. If you don't find the microphone, please use the Discord channel and type in your question there. There is already a question that came up. How do you quantify the quality of an embedding? And the second question, is that quantification comparable across the quality of 1D versus 2D embeddings?
Yeah, thank you. It's very interesting questions. In the literature, there's a lot of such a measurement to evaluate the qualities of an embeddings. But in particular, here in our papers, we would like to look into whether an embeddings preserve the neighborhood, in particular the clusters, and we as I presented or in the presentation as well, if you can look into our papers, we apply the silhouette coefficients that measures how well one element locates in the class that it's supposed to belong to. And then if this silhouette coefficients measure and is outcome the positive values for elements that's really located in the embeddings in the class is supposed to belong to, and is have negative if the elements is projected very far away from the class is supposed to belong to. And then we count the frequency of positive numbers in the embeddings, and then that's exactly the outlier index that we use to judge if the embeddings preserve well the clusters. And the second question, can you
The second question was, is that quantification comparable across the quality of 1D versus 2D embeddings?
Yeah, it's interesting question. Yes. I think in general, 2D embeddings is always better than 1D embedding. And we would like to make the point that we see some looking into some data set, and we see that there's some problem with the 1D embeddings, and we take into this into account to motivate us to look into our approach, like try to involve user into the pipeline. And and then we see that because the 1D embeddings, there's so many factors that we right now at this current point cannot answer mathematically so why it happened like this, but only some empirical observations that lead us to the work for this. And we see that like factors like a low degree of freedoms, or maybe some or the cost of dimensionalities, maybe, who knows. But with the data set, we see that there's some problem with the 1D embeddings. That's why it motivates us to work with our approach. Yeah.
All right. I think we are perfectly in time now, and we have answered all the questions from the Discord. Thanks a lot, Quynh, for the presentation and for the discussion. I clap my hands.
Thank you
Everybody
very
claps
much.
hands.
Thank you very much.
Thank you. And we move straight on to the second presentation. And the second presentation, the title is Data Reconstruction from Colored Slice and Dice Treemaps. And your authors are Markus Henkel, Volker Knauthe, Tatiana von Landesberger, and Stefan Guthe. And Markus is going to give the presentation.
Yeah, thank you so much for the introduction. So yeah, as you've heard, I will talk about the work that we've done on the reconstruction of data from colored slice and dice tree maps. So let's begin by talking about tree maps. Tree maps are visualizations for hierarchical data, and one of their advantages is, of course, that they're particularly space efficient. So they can show large amounts of data without running out of display space. They show the weights of nodes relative to each other. So for example, a rectangle with, let's say, twice the area represents a node with twice the weights. One of the disadvantages of tree maps is that they only show the hierarchy implicitly. Then, of course, there are a lot of different metrics that are used to assess the quality of tree maps. Some examples include change or readability metrics, but there aren't any metrics that are concerned with ambiguity in tree maps yet. And of course, a lot of different construction or layout algorithms exist as well for tree maps. Each of them works differently and has different goals. And in our work, we've begun with the very first one, which is the slice and dice layout. So as you can see right here, it's fairly simple. Essentially what it does is it begins with the outer rectangle of the tree map, or the outer boundary, and then it divides it into smaller and smaller pieces by drawing vertical and horizontal lines based on the structure. So when we look at the tree on the left, for example, we've got these 4 child nodes of the root. And because of this, we have to divide the tree map into 4 of these vertical slices that we can see right here. This process is then just repeated for each of the child nodes or each of the nodes. And we always alternate the direction. So in the beginning, we draw vertical lines. Then we switch to horizontal lines right here. We go back to vertical, etc. So essentially going from a tree to a tree map is pretty simple, but what if our input and our output were reversed? So what if we were given a tree map and we wanted to see how the original hierarchy looked like as a tree? Well, the basis of our reconstruction algorithm is the following. Essentially what we do is we search for divisions or look for divisions of the tree map. So again, we've got these 4 vertical slices right here. And because of this, in order to reconstruct the tree, what we have to do is to essentially add 4 child nodes to the root of our reconstructed tree. And each of them will, of course, represent one of these slices. And then similar to the construction, we also continue this process for each of the smaller parts and each of the subsets of rectangles. So in the beginning, of course, we've divided the tree map into these vertical slices. Now, the next step, we search for horizontal lines, like here, for example. So right here, this one splits this part into top and bottom. So again, we have to add 2 new child nodes right here. So the general idea is essentially that we search for divisions, we divide the tree map into smaller parts, and based on the structure, we have to add new child nodes in the right places. Now, the problem is that there are actually multiple ways of dividing the tree map. So as you can see right here, we only have 3 of these vertical slices, and this is why our reconstructed tree looks different as well. So tree maps can be ambiguous. And essentially, if we see a line in the tree map, we can't really know if that's one line or if it's multiple lines that just seem like they're one. So it could be a line, but it could also just be a coincidence. And as we've seen before, these different divisions lead to different subtrees that we can reconstruct. So in the top tree map, again, we assume that this left vertical line is a line, and in the bottom, we assume that it's just a coincidence. And this is not just tricky for the algorithm, of course, but even for us as humans, it's not clear which of the divisions is the correct one. And furthermore, this process of finding the correct lines and finding all the correct divisions is not quite as trivial, because as I've said, for each line, there's always the possibility that it may or may not be an actual line. And that's fine for small tree maps, but it essentially leads to combinations of power sets, and that really doesn't scale well into larger tree maps. So what you've done is to come up with a way of efficiently finding all the correct divisions so that we can reconstruct data even from way bigger tree maps. But I won't talk about the actual details for now. Either way, as you might have already guessed by now, this problem always occurs when you have these cross-like structures in the tree map. And basically for each of these spots, there are two different subtrees that make sense. And in the end, we have to combine all the possibilities. So for this tree map, there's a total of 4 different trees that we can reconstruct. Now, even though we can reconstruct these efficiently, the fact that the ambiguity is multiplicative still means that for some tree maps, there's quite a large amount of trees that we can reconstruct. So just to put things into perspective a little, as you can see, a simple 5x5 grid already leads to more than 7,000 different trees that all fit the same tree map. And in fact, a 10x10 grid leads to really an incomprehensible number of trees. Now, obviously, these grids are extreme cases, and not all our tree maps are going to look like grids. But some ambiguity is actually pretty common in tree maps. So as you can see here in an evaluation, we found out that the chance for a tree map to be ambiguous largely depends on the number of leaf nodes. So for smaller tree maps or very small tree maps with around 25 nodes, it's not a big deal. But as tree maps become bigger and bigger, the chance for them to be ambiguous rises as well. And at 400 or even 800 leaf nodes, almost every single tree map will be ambiguous. So this is a pretty common issue. But let's go back to our simple example from before. As we've seen for this tree map, there are these 4 trees that we can reconstruct. But now, even though we can reconstruct all of them, we can't really tell which of them is the original. And that's not really satisfying. At the same time, we've only really looked at black and white tree maps so far. But what if our tree map were colored instead of being black and white? Well, it turns out that colors are used pretty commonly in tree maps because they can easily show additional information. So what we've done is to essentially look at 5 different color schemes and try to find out how these color schemes could somehow improve the reconstruction. So let's talk about each of them really quickly. The first one is one that we refer to as attribute colors. And the perfect example for this is, imagine you wanted to visualize the file system on your computer. You could do that and come up with a tree map. And then you could say, well, I want my MP3 files to be blue, for example, and my text files, for example, to be green. So it could look like this. The second color scheme is called main branch colors. And as the name suggests, these allow us to quickly tell different main branches apart. The term main branch essentially just means the first division or the first slice in the construction. So here we can easily see that these 3 purple rectangles belong together and the 2 green ones belong together as well. Now, what the remaining 3 color schemes all have in common is that they all encode the depth of nodes in the brightness. So essentially, a node on a higher level will be brighter and a node on a lower level will be darker. So the deeper the node, the darker the color, essentially. We combine this with the previous 2 schemes. So we have attribute colors and we have main branch colors with brightness. And the final and the 5th and final color scheme is the so-called tree colors color scheme. And the main goal of tree colors is basically that similar nodes are supposed to have similar colors. So for example, if we have 2 sibling nodes, or if we have a parent node and a child node, these are in a relation, and that's because of that, they are supposed to have similar colors. Then there are some additional parameters that can be tuned to change how tree colors look, but we'll just leave it at this for now. Either way, now that we've seen the different color schemes in action, how do these actually help us improve the reconstruction? Well, let's look at our favorite tree map again. This time, instead of being black and white, we've used main branch colors with brightness. And now the basic idea is essentially that we can reconstruct the same 4 trees, but we also save the colors of the corresponding rectangles. So the reason why this still works and we end up with the same 4 trees is that the colors don't really change anything about the structure. So you can see all these lines are still in the same position. And because of this, all these crosses are also in the same position. So we can come up with the same 4 trees pretty much. Now our approach is to essentially look at these colors or these color trees and try to reject as many of them as possible if they don't match our color scheme. So let's look into this with a little more detail. As you can see here, the first case I think is pretty obvious. In the left main branch, we have both purple and green nodes for both of these trees, and that doesn't fit our color scheme because if we've used a main branch color scheme, these nodes should all be green or they should all be purple. We couldn't have green and purple in the same main branch. So both of these trees can be rejected. This case, the second case, is a little different, and essentially what happened down here is that these blue nodes and the orange nodes are obviously on different levels, but they actually contain the same exact brightness. And that doesn't fit our color scheme either, because if those nodes had the same brightness, they should all be on the same level, which is not the case here. So same thing as before, we can reject the tree. And in fact, for this tree map, we've already rejected 3 out of 4 trees. So we're only left with this single tree right here. And because of this, we can actually say that this tree must have been the original that was used to, visualize this tree map. I also want to very quickly mention that for these brightness checks to work, we do need some prior knowledge, and that is that the main branches must have all started with the same brightness, because otherwise we could still compare blue with blue and orange with orange, but we couldn't cross compare them anymore. So that's just something to keep in mind. Of course, we've then evaluated how well our approach works. So essentially, we have varied 2 weight ranges for our nodes, and we've varied 6 different amounts of leaf nodes. Then for each of these conditions, we've randomly generated 1,000 trees. We've applied all of our color schemes, and we've visualized them as slice and dice tree maps. And then based on these colored slice and dice tree maps, we reconstructed all the tree data and evaluated how well our color schemes can reduce ambiguity. So the first thing we've seen is that attribute colors without brightness don't help us whatsoever. They simply don't add any information about the structure of the hierarchy, so they're not useful for the reconstruction. The main branch colors without brightness help us in some cases, and you can sort of see this in the box plots right here. When you compare the gray and the blue boxes right next to them, they're roughly in the same places most of the time. Occasionally the main branch colors help us a little bit, but they don't generally make a big difference. At the same time, we've also seen that all of our color schemes that encode the depth of nodes are actually extremely useful, and in fact they can almost always perfectly solve the ambiguity. So in most cases, we can actually reduce or reject all trees except for the original one. So these work very well. To quickly summarize everything, we've seen that ambiguity in tree maps means that different trees can fit the same tree map. We have come up with an algorithm to efficiently reconstruct tree data from a given tree map. And we've seen that certain color schemes can help us reduce the ambiguity, especially so if they somehow encode the depth of nodes and the brightness. As for future work, obviously we've just focused on the slice and dice layout algorithm, and we focused on 5 different color schemes, but there are many others. So it would of course make sense to explore additional color schemes and also find reconstruction algorithms for different tree map layouts. The third point I've briefly mentioned or briefly touched upon, essentially this tree colors scheme comes with quite a variety of parameters, and it would be interesting to see if we could find optimal settings for these color parameters in the sense that they reduce ambiguity as much as possible. And finally, of course, in this entire work, we've just focused on this entire problem from an algorithmic perspective, but it would also be interesting to see how humans can actually read and understand ambiguous tree maps. Yeah, so that's it from my side. I thank you for your attention, and we can continue with the discussion.
Thanks a lot, Markus, for the presentation. We already have a couple of questions popping up in the Discord. I start with one by Helwig Hauser. He wrote, I may have missed it. Any reason for not including nested tree maps into the comparison?
Nested tree maps are definitely an interesting idea as well, and that's also something we could do for future work. But so far, we've just begun with slice and dice tree maps without the nesting effect, because of course it's just a simpler and easier variant and the very first one. But that's definitely something that could be done in the future as well.
Okay, there's another question by Shivama Agarwal. Using colors to make tree maps unambiguous works well, but the scalability would be limited then, right? It's more a rhetoric question, but anyway, it's a question.
The scalability, in the sense that you only have a certain amount of colors. I assume that's what the question is about. Yeah, makes sense, definitely.
Okay, there's another question. How about removing the ambiguity in tree maps by having a varying padding based on the level of the node hierarchy between regions of tree maps?
I think that's essentially just what nesting is, if I understand the question correctly. So yeah, same thing as nesting.
Yes, I think so. All right, are there further questions? Yes, Helwig again wrote, shouldn't this be also seen in a cost-benefit situation? Using color for depth takes color away from representing node attributes, for example, as it is often done. Could such a cost-benefit ratio be measured?
Yeah, I think that's a really interesting question, actually. It's a very good point. So obviously, oftentimes colors are used for different things, especially the hues usually. So if we also use the brightness to indicate different attributes, then that's true. So we have to essentially choose what we want to do. Finding a cost-benefit ratio would be interesting, but we haven't really thought about that. We've just looked into the case where we do have the color and we do have the brightness, and we can use it to reduce the ambiguity.
Okay. All right. I don't see any further questions now in the Discord, and we are pretty well in time. So thanks a lot, Markus, for the presentation and for answering all the questions. I clap hands again. The world claps hands. And we continue to the next presentation. And this is actually an invited presentation, Michael Sedlmair. And the title of his talk is Machine Learning Meets Visualization. And for this, we meet Michael now with your presentation. Let's get started, Michael.
Hello, Holger. Hello, everyone. Good morning. So my name is Michael Sedlmair, and I'm gonna talk about, as Holger announced, about machine learning meets visualization. So we'll see how that works. So usually for those who have seen talks of myself before, I try to do interactive talks with the audience. So as we know, this is a bit harder in this virtual situation, but I think it might still work. Okay, so what is this all about? So the big motivation behind, I guess, all of our work is the growing amount of data. I still love this slide. I keep it. I think I used it first in my defense 10 years ago, and like it's still valid. So when it comes to describing what we are doing in my group, I usually like to use the term human data interaction. It's really about data that is made available for people. So visualization, visual analytics, these are great tools, but there's other tools that we need to enable people to understand patterns, to gain insights into their data, make decisions, or communicate their data with larger audiences. So as we know, there's like, two really big components in that game. And the first one is really interactive visualization. This is what we all love to do because sometimes humans can see patterns that algorithms cannot. And here is this this great new example of the Anscombe's quartet that was published at Chi 2017, where you see like different data sets that obviously to a human observer look very differently, but it has the same statistical summaries in terms of the X and Y means, the standard deviations, and the correlation. But like as humans, we know these are different patterns that we're seeing. But at the same time, data analysis, human data interaction is not possible without algorithms, and specifically with algorithms that are produced in the data mining and the machine learning communities. So why do we need these algorithms? Because they can reveal patterns that humans cannot see. And I think like I want to come back to Quynn's very nice first talk today in the morning. It was very early, but some of you might have seen it. Dimensionality reduction. We just as humans, we don't have high dimensional eyes. So we need to have some algorithm, some dimensionality reduction method, for instance, to unroll some high dimensional manifold before we as humans can look at that data. And so this leads to this question of like, what is actually the interplay between these like algorithmic components or machine learning components and the visualization. And a lot of our work has been dealing with that question. And today I want to like talk and discuss this intersection a little bit from two directions. In part one, I want to talk about what visualization can do for machine learning. So if you work in machine learning, you can now pay attention and hopefully learn something about how you can use visualization tools to get better insights into your models. But then I will also argue, and this has been not so common for the last 2-3 years, I think we're seeing more things also using machine learning modeling approaches for doing better visualization, design, and research. I think there's like a huge potential in this area. And then I want to conclude with some general research challenges at those intersections. Okay. So let's start with the first part, which is visualization for machine learning. So as we know, explainable AI has kicked in. So all of a sudden, like, machine learning, like starting 2012-ish, has gained like, a huge attention in the general public, in politics and the society and industries. It's changing the world. Data is becoming the new oil of the industry and that sort of stuff. And now like people ask for, like, we need to have explainable models. That's a huge topic. There's lots of funding in these areas. And so visualization is obviously, at least from a visualization perspective, a key factor. But this is also true because like if you just go out and then like, I'm not taking examples from the Viz community per se, but other people are talking about, they're using visualization and interactive visual analytics tool to help people gaining insights into these black box models. So here, like, explain gradient descent, arguably, that's not necessarily just a machine learning technique, but like, you can use visualization to greatly and like, very easily explain what's going on here. Or like, TensorFlow, a little bit more complex. You can use visualization to interactively explore what works and what doesn't. So those are great examples. So our focus in that realm has been a little bit different. So we're working on solutions that are more agnostic to the type of models and are more like, outside and like working with ensembles of different models. So we called it visual parameter space analysis. And so the core problem we're really dealing here with in terms of machine learning is that we want to understand and select a good machine learning model among many other models. Okay, so to give you a concrete example, I want to go back to this example that already Quynh talked about in his first talk, using dimensionality reduction. Why? Because dimensionality reduction is something that like we in visualization always deal with, and we need those tools. And so like having some solutions of like, finding good dimensionality reduction method is also good for us as visualization people. So we remember a dimensionality reduction is this easy process. So we start with some like high dimensional data, let's say about cars, and then like, you know, we reduce it with some cool fancy dimensionality reduction algorithm, PCA, MDS, TSNE, ISOMAP, UMAP, you name them. And then usually we as visualization people, we reduce to 2 dimensions, and then we visualize that data, for instance, in a scatter plot, as we have seen in the first presentation. So the question now is, which dimensionality reduction algorithms do I want to take? And if it's parametric, how to set the parameters in a way that I get the results that I want to have. So let's look at the traditional approach, which is usually trial and error. And for those of you who are working with DR, dimensionality reduction, you probably did that at some point in your life before. Okay, you use some algorithm. PCA is pretty famous. It's the old one, and you look at the data, you're unhappy. So then you try something else. Say you heard about TSNE, which has been like the new and like the cool kid on the block for the last 10 years. Now it's taken over more by UMAP. But so you try some parameter setting. That's also not what you want to have. And then you try some other parameter settings. You're still unhappy. And like you have this unsystematic approach to like sifting through a lot of potential solutions to your problem, but not really getting to the one that you really want to have, or like to understand this space of possibilities in a systematic way. And this is exactly what we propose to use visual parameter space analysis for. So instead of like sequentially trying out different algorithms, the idea is really to sample the space of algorithms and parameters, create the results, and then have a visualization interface that allows you to look at that space. So very often we use some sort of like, you know, similarity map. So we have like, for instance, a meta MDS map where we can then plot all the results of the algorithm outputs into a map again. And like, you know, here in that case, the similarity would be encoded by the distance. So if something is close together, you can see, okay, those two solutions would be similar. And you see the user is smiling now, of course. Okay, so here is like, you know, one of the tools that we have built for using visual parameter space analysis for dimensionality reduction methods. So here, let me quickly go through like, you know, a little demo video here. So the tool has many other facets, but this is really this aspect of visual parameter space analysis. What we see in the center here is really what we call this meta map. So this is what I just explained. In this case, we're using TSNE, not MDS, but like every small dot we're seeing here is a scatter plot that resulted from using a specific dimensionality reduction method with a specific parameterization. And so here on the left-hand side, we see actually the parameterizations that we use for these dimensionality reduction algorithms. So you see, we used ISOMAP, MDS, PCA, and on top, where you see that white box, we use TSNE, which has 2 parameters, the perplexity and the epsilon. So we have a 2-dimensional parameter space, which we color code, and then we also use the colors in the main map. And now we can like leverage this entire pipeline of interactive visualization. We can specifically do like, you know, drill down into details, look into how these scatter plots are actually, these dimensionality reduced scatter plots look like, and try to understand similarities and differences between those. And linking and brushing, our favorite interaction technique in visualization, can also be used to now understand the relation between the input parameter space on the left and the output parameter space. And here we can do interesting things. So now we do range selection. We highlight on the left top the TSNE parameters that were used here. And here I stop for a moment. We're seeing some interesting things. So we're hovering over that space and we see scatter plots, so projections that reside in the same visual space here, meaning they're visually similar. They seem to have similar perplexity values, but they have to have seem to have epsilon values that are all over the place. So that's interesting. We can actually also do that the other way around. We now select a perplexity value and we hover over that, and we see like this really relates to the smooth transition of visually similar projections that we get. If we do the same for epsilon now, we see those are all over the place. So we can learn something about the sensitivity of the parameters here. So we know now know that perplexity seems to have like a very smooth transition. So there is a good sensitivity in terms of that parameter when it comes to the visual differences of the projections that we're seeing. However, epsilon is highly sensitive or not sensitive at all. And so it's all over the place. So there seems to be little influence of the epsilon to the visual appearance of the projections that we're seeing. So the idea of visual parameter space analysis is really a general model agnostic one. It's not a model specific tool that we're seeing like in other and very, very useful approaches that have been presented in the last years to dive into specific types of models. This approach can be really used for all sorts of input-output models. I've seen Helwig Hauser has asked a few questions beforehand. He also uses that approach, and I think very successfully for really great tools. And it's really helpful, but it's a little bit different from the classical visualization perspective, where you would, at least in InfoVis and visual analytics, very often start with the data. Here we actually start with the model. We sample the model, then we create these overviews, and then we allow the user to understand this model space. So historically, I would argue this is mostly coming from the simulation sciences, and also from like, just algorithms are usually input-output models in some way. And so we have used it, for instance, what you can see here for image segmentation algorithms. You can guess what that is. On the left, we have like a brain scan. Okay, so this is what people might have like guessed. On the right, we have a one-dimensional projection of bird simulations, bird flocking behavior over time. And so like these are models where we use this approach. We like, created ensembles, and then we used visual parameter space analysis to help domain experts understand their models and make the choices here. Many, many other people have used it very like successfully, I'd say, and like, in a very inspiring way, as I put here some examples of like, for instance, exploring models that help you create explosion animations for movies, or like design parameters of like an insertion needle for medical purposes. So there's really a lot of great examples here. So what we in my group have set out for the last 6-7 years was really trying to explore that approach for machine learning models. So I showed you that example of dimensionality reduction, but there's many other ones. So indeed we started out with clustering in the first place. We never published that. That happens sometimes, but I think it was a great tool that already included a lot of the initial ideas that we now also have in tools like the VisCoder, the dimensionality reduction tool that I showed to you. We actually also did that for classification. So here we see in submission, that's not true anymore. The paper is presented in parallel at the AVI conference, which happens online at the same time. The presentation, I think, is given at the very same time as my presentation. So if you get bored, just switch over, but I think you have to pay some fee to attend AVI, not for VMV. Okay, and we also used it for active learning. It's really a cool approach that you can use. And why do I think it's just this like, very general and nice framework that we can use here? There's a couple of reasons. And one reason is I think there's like some great analysis tasks that this framework is supporting. First, it's supporting multi-objective optimization. If we have single objective optimization, ask Holger, that's easy. We just use math and then you get the perfect solution. No need for a human in the loop. But like if we have multiple objectives and some of them not even well defined, maybe visual parameter space analysis helps you to find the best parameter for your model. Sensitivity analysis, which is basically understanding how much variance is caused by varying in the output by varying the inputs. This is exactly the example that we looked at in the VisCoder demo before. Partitioning, how many different types of model behaviors are possible? So this is essentially the classical clustering approach. We can look at clusters in the output space and learn something about the potential of the model or the ensemble to create different behaviors here. Outliers. So what are the one-offs? This can be really insightful in terms of like, for instance, improving your model. It might be like incorrect, or also like, understanding like anomalies that you might create with that model. So there's many more things, but I want to stop here. So we're halfway through, and now I want to like turn to this other example, which is machine learning for visualization, which I think has gained a little less attention so far in the community, but which is, in my humble opinion, similarly important. Okay. So you're Viz people, and this is one of these interactive exercises now. So like we're seeing here some data, and now we need to visually encode that. And so what do people generally do outside in the world if they haven't known about the Viz community? They go to Excel and they get, for instance, like a 3D bar chart. Who can see the pattern? Okay, now it's actually the time where people talk. Okay, I can see it, I can't. Okay, it's hard. But like, let's now encode it instead of a 3D bar chart as a heat map. And you can see the pattern now. Everyone. It's this question mark in the middle, which is invisible in the visualization before, because we just picked the wrong visual encoding here. And so I'd say this has been a core challenge in the visualization research for the last 20 or 30 years, specifically InfoVis. We see a lot of user studies traditionally that try to derive guidelines, and this has been the traditional approach that help to guide designers towards good and effective and efficient visual encodings. Like here, the great paper by Gonium and Jean-Daniel Fiquet from a few years ago, where they compared matrix visualizations with node link diagrams. However, there's an issue with guidelines, and guidelines, they're great, but essentially what they are, they're rules of thumbs. We can't really formalize them. We can't put that into like an algorithm that we would like to use for like automatic optimization of these designs. And so this is something that has started like 10, 11 years ago, or like actually 14 years ago, with work by Enrico Bertini, where like, the idea is let's use measures that can help us to depict how humans would see certain patterns in data. Okay, so let's use the scatter plot example here again. Why scatter plots? Scatter plots are the fruit flies of visualization and research. They're complex enough that we can do something meaningful, but they're simple enough so we still can understand what's going on. So let's say we want to now model how a human perceives class separability in a scatter plot. Okay, that means like is a certain class, the blue class and the red class, for instance, are they separable or are they mixed together? And we now want to have an algorithm that is actually modeling that. And here was like, this one by Mike Sips from 11 years ago, which is also a paper co-authored by Pat Hanrahan, who our Turing Award winner. That's really cool. So the idea is simple. So we compute for each of these classes, we compute the centroids, and then we iterate over all the points. And then for each point, we basically check what is the closest centroid. And if the closest centroid is your own class centroid, that's something good, and the value of this metric would go up. If it's, like in this case, the red point is closest to the blue centroid, this is something bad, and the value of the metric would go down. So what we essentially would do, we iterate over all points, and then we normalize the value, and then we get like a separability score that we can use to find like, separable scatter plots. I will come to examples why this is important later on. So for instance, like, here in this scatter plot matrix. Okay. The main limitation, however, of these heuristic-based measures that we used in our own work is low generalizability across data sets. What do you mean by that? So we set out and we wanted to use it on many different data sets that we had on our own. And we found, oh gosh, the metrics don't seem to work well. There are some certain assumptions about the underlying data that these metrics, these heuristic-based metrics, make them not a good choice for many data sets. So here we did what we called a qualitative data study, where we looked at 816 different scatter plots and used these metrics and qualitatively judged how well these metrics did. And so if we, for instance, only look at the almost 300 real data sets, scatter plots from real data sets, that we saw that the metrics failed in almost like 68% of the cases. So there's a need to do something different. And then that was the time like 7 years ago, when I started to talk with my colleague Michael Opetit, who said, hey, isn't that essentially a computer vision machine learning problem that we're facing here? And please forgive me if you're a computer vision person on my simple view on computer vision research, but for me, it's essentially, there's cats and dogs, okay? And then what you want to do is you want to build an algorithm here, or R2D2, that gets an image of like an unseen animal, here a cat, and then like the algorithm automatically can classify that this is a cat. Isn't that essentially what we also want to do for abstract visualization? So we have some scatter plots that have separable classes and some that are having mixed classes. And essentially what we want is we want to feed in an unseen scatter plot, and then our algorithm, our model tells us this is separable or not. So this is what we did, and we wrote this Euroviz paper about that. So really simple first approach. We gathered a large collection of ground truth data from some human coders. They really just said a class is separable or it's not separable. So it's really just a binary classification problem. Then we can use like different models or measures here to predict these human judgments, and then we can simply evaluate the quality of each of these models by like essentially saying like how well like does this model match with what the humans say. And this is basically what we did without diving into the details here. So like we are seeing here a plot of like, I think that was like, 30 something measures that we identified that could be used for that. And on the x-axis, we see the area under the curve bootstrap value, which essentially means that like 50% is a random guess in this binary classification problem, and 100% would be the perfect prediction of the human. And it turns out that the centroid measure was actually the best, the one that I presented before. So there's a few reasons for that. So we really just picked like very clear-cut examples for the evaluation and the training and the evaluation set here. And so the other reason is like there's 82% average AUC, which means there's still 20% of improvement possible. And that's actually what we did then. And now it's pretty cool because now you can, you have this automatic framework, machine learning based framework that you can use to evaluate these metrics. So what we did is not just creating one measure, but we systematically explored the space of 2002 measures through this systematic approach. So we used like different proximity graphs, and that's lots of fun, I can tell you. So there's Delaunay graphs, there's KNNG graphs, there's different ways, and purity functions, so ways of how we can tell the separability based on these neighborhood graphs. So we found that here, like 58% of our new 2002 measures outperformed the centroid measure, which is the pink line in that graph here. And that the best measure that we actually got had an accuracy of almost 93%. And like even ones that are computationally very simple got up to like, 92% average AUC. That's pretty cool. And it would not have been possible as classical user study type of evaluations that we have in visualization. Okay, now you say, okay, Michael, scatter plots, fruit fly, I got that, but like what exactly can we do with that? So I showed you that example of like, picking good views in scatter plots before. This is nice, but you might think like, okay, 5-dimensional scatter plot, really, are you that lazy? Yes, I am. But like if you have 10-dimensional data sets, we have like 45 views, still not a problem, but like, there's this explosion. If we have 200 dimensions, we already get like, 20,000 views that we would manually sift through. And this is nothing that people want to do. So like, this is a way to use these metrics. But there's many other cool things that we can do with metrics like that. And a lot of our work, specifically with Yunhai Wang in China that we have done in the last 3 years, was about using these metrics as an optimization criteria in visualization problems. So for instance, here we can create new dimensionality reduction methods. So we use these metrics and the ones that we created from the human perception as an optimization criteria in a linear dimensionality reduction framework. And we created an LDA, linear discriminant analysis, like dimensionality reduction. And in our evaluations with humans found that the ones that we created, so our dimensionality reduction method, actually created more separable projections than LDA for humans. Okay, we can also, of course, do other tasks. So like this is a recent work where we finally got rid of the colors and we just look at clumpiness. And clumpiness is one of the skagnostics. And we found that with this like data-driven, human perception-driven framework, we get better results than, for instance, the classical skagnostic clumpiness. We also can use that, for instance, for like modeling color perception. So here we use that to automatically assign colors to classes in a scatter plot. And of course, it's not just for scatter plots. Scatter plots are fantastic, but there's like many other visual encoding techniques like Treemaps, as we have seen in Markus' talk. So for instance, we're using that at a paper that we're gonna present at the end of the month at InfoBiz for stream graphs as a way to automatically optimize, based on human perception, the order of streams in a stream graph. So there's a lot of things that you can do, I would argue, with that. Okay, so let's conclude with the third part, the research challenges. Just let's like try to look a little bit forward. So today I talked about visualization for machine learning and machine learning for visualization. But as we all know, the holy grail is visualization and machine learning. So we need well thought out interactions of human and computers to solve our most pressing problems. This is a quote by Michael Jordan, not the basketball player, but the like famous stats professor at UC Berkeley. And I full-heartedly agree. And this is what the visual analytics community has been trying to do. And also in my own work, this is when we work with domain scientists, that seems to be like, you know, the way to go. So here's an example of like early work from my own PhD, where we used an approach like that for in-car communication process analysis for like these network communications, but also recently with Manu Waldner here on the right, where we organize documents in a space and automatically create suggestions by the system, like, you know, to organize. It's really this like, you know, human data, human model interaction that we're leveraging here. Second, it's really these interdisciplinary projects that we need to do, and like machine learning and visualization together with domain scientists. And there's something funny going on. If you now look and you want to become a data scientist, that's great because you get a shitload of money. But like, if you look at the announcements, you basically need to be a genius. You need to be like, you know, math, perfect, programming, databases, domain knowledge, soft skills, communication, visualization. That's a whole lot of stuff. So the way that we're going is a little bit different. So we have this paper on design study methodology. We take a completely different role. So we're defining roles. We want to have like interdisciplinary projects. And like, we're thinking about like, how can we bring different people together and like allow them to create the same language to efficiently and effectively work together. I think this is definitely an alternative approach to like, you know, one person needs to learn everything. Machine learning based visualization design. So this was essentially the part that I talked about in the second half today. For me, this really seems, I know that's a hard word, but it could be a new paradigm for doing visualization research. Why do I think that? So if we look out in the world, like it has changed. So scalable data becomes now available. So some of you might have seen this great paper, the VisNet at CHI 2019, where they collected like 31 million data sets crawled for the web that we could use for approaches to like model human perception on these data sets. At the same time, we have more and more scalable methods. So like our studies are not in the lab anymore, but many of them are online on Mechanical Turk. Not that like this is easy, but like essentially if you throw some money at that, you get very quickly like, you know, a lot of feedback from human users on perceptual tasks. And we remember there was like Jeff Harris' paper from a long time ago on CHI, where like they showed that like perceptual tasks, Mechanical Turk studies are really good. At the same time, we also get like new machine learning and deep learning models from that height. That's great. There's like a whole bunch of new models coming out essentially every week that we can leverage for modeling visualization perception. The fourth challenge that I want to put out is really, which I think is sometimes getting a little bit lost in our community, progressive data analytics and like just scalability. It's not it can be like, or should be repeated much more oftenly. And scalability is a huge deal in our community, much more than in other communities, because if you want to show your data to people, ideally you need to react in milliseconds to create these interactive rates, but at least in seconds to have analytical rates. And so I think with really large data sets, that's just not possible. So we need to think about solutions that help us to progressively load data. There are some threats that come with that, but there's also some benefits to keep analysts in the loop. And fifth, so this is some stuff I have been, there was a panel yesterday about immersive analytics, and also our own recent work has really dived into that. I just want to show that here. There's really this novel displays, novel types of interactions that is getting big now again, which I think is really important. And again, also sitting at the intersection of visualization and machine learning here. Immersive analytics, situated visualization, where we put that into the real world context, but also new interactive ways like using haptic feedback or using eye tracking, that sort of stuff. And we all know the potential of those things for visualization, but machine learning is an essential part of leveraging these types of input technologies for not just regular HCI, but of course also for us in visualization. Okay, so let me conclude. What did we talk about today? First, we looked at visualization for machine learning. I hope that I could show you some reasons why visual parameter space analysis might not be the worst idea if you work with people from machine learning. And then we looked at machine learning for visualization. To put it boldly, this will automate our fully optimize our design. Of course, we know this is going to be a semi-optimization process, not full optimization, but there's a lot of potentials in that area. And then we briefly scratched on 5 challenges that I see in this realm of visualization and machine learning. Why is this also cool? This is my favorite last slide. So visualization is awesome because telescopes and microscopes, we know they changed how people see the world. What you guys are doing today is we're creating all these visualization tools that help people seeing the data and understanding the world in a new place, in a new way. So thanks to my group at the University of Stuttgart here. Without them, lots of the stuff that I showed today would not have been possible. And also, of course, to the many other collaborators and students that I have been in the great honor of working with over the last few years. On that note, I want to say thank you very much, and now I'm happy to take any questions.
Thank you, Michael. It's very safe to say that this was a truly inspiring talk, and we have time for a couple of questions. There are already some questions coming up. Let's get quite a lot of them, so let's see if we can go through all of them. Thomas Schulz, for instance, is asking, algorithms such Theisel are non-deterministic, so even the same parameter setting could lead to very different visualization. How should approaches for parameter space exploration deal with this?
This is a great question. Thank you. Thomas was the one who asked the question.
Yes.
Thank you.
Thomas.
Great question. Yes, I think even here, visual parameter space analysis can help. If you have a non-deterministic model, you essentially, whenever you plug in the same parameters, you might not get the same output, right? And so if you now just say you sample that space, you let run your tool, your dimensionality reduction method, T/E, for instance, 1,000 times with the same parameter setting, apologies. And then you can create a visualization that gives you an overview of the variants that you have created. It allows you to understand what the role is. And so T/E is really interesting here because it's also an iterative method. So you could also use that approach over time, of course. And as you know, T/E, often you start using it and there's forming something, and then boom, all of a sudden it substantially changes. By the way, this is also related to progressive analytics and the threats that we might face there. So this is, I would say visual parameter space analysis can help to understand these non-deterministic models better and the potential problems that can stem from them.
Okay, there's another question from Helvig, actually, about the first part of your presentation, you clearly have something for trial and error users of machine learning. What do you offer knowledgeable data scientists who know their tools, that they do for which use case scenarios they are designed, etc.? And Helvig adds, it's slightly provocative question, of course. You are welcome. You know Helvig, and you might find an appropriate answer for this.
Provocative is always good. So thank you very much, Helvig, for that provocative question. I think it's not highly provocative. As we know, so the examples that I showed today, so this tool was created really for educational purposes mostly. This is the target audience that we had in mind. But visual parameter space analysis works similarly with like expert users. Like, I think there is nothing like, I completely know all my tools. Just to think about like totally different area, like, AI creativity. So using creativity, boosting algorithms, machine learning algorithms to help people like generate a new song or generate like a new piece of art. It's the same for data scientists. Like, even if you know everything, that doesn't mean that you know all the potential solutions at that very moment in time. You might forget something. And I think like, even if you like, if we assume the perfect user, the president of the United States thinks he's one, for instance, we might still need to see a visual overview or gain a space about like, the ensemble. That's just not possible by like sequentially going through, because then you need to load everything into your head and remember everything. And this is the classical like perception beats cognition, right? We compute everything, and then like you get an overview, and you get like a systematic approach. Even if it's just a one-dimensional plot that you can generate about these ensembles, you get something valuable that's more just than the single pieces that you created before. And so, of course, I have a cynical comment for Helvig. You probably know that you just asked this question for sparking some great discussions. But I think like, it's really with domain experts, we need to work together and like create these tools together. And usually the tools are much more complicated. The papers are harder for us to write because we need to reveal all that potential. That's why our initial paper that's presented today at ABI got rejected at Kai. We work together, for instance, here with natural language processing domain experts. And they already, like in the beginning, they also said, okay, like we know all our tools and that's probably not useful. But like then they actually used the tool and they used visual parameter space analysis on their mods, and they found quite some cool, interesting things. But like the complexity of the tool and the usability of the tool, I would say complexity is higher, usability is lower.
There is another question by Helvig about the second part of your presentation. How do you distinguish a false positive with respect to separability from the one good algorithm that successfully solves a hard problem?
Okay, let me try to understand that question. How do you distinguish a false positive from the one good algorithm that successfully solves a hard problem? Okay, so this is a tricky question. I see beyond lovely talk. Thanks. So I think what you're referring to here, Helvig, is like, and please correct me if I'm wrong, but it's like my algorithm might produce something that looks great, but it's not the truth, right? This is like, a false positive. Specifically in dimensionality reduction, we have that. And so like what my classical answer to that question is like, what we're doing here is really, we're trying to modeling human perception. So in that case, we don't have that type of false positives per se in that small framework that we're thinking about. So we're just like, is this how human perceives that scatter plot or not? So that's a different type of false positive. But in that case, I think our models work quite well. But the big threat, of course, is like, what if like the projection in the beginning already has been flawed, right? And then like, it's a tricky question. What we do is usually then we compute metrics in the high dimensional space, we compute metrics in the low dimensional space, and then we compare them. If they both say like, good, then it's a sign that like, the chance of a false positive is low. It doesn't mean that there's no chance, by the way, but like if they disagree, like if you say like my metric in the high dimensional space says there's perfect clusters, but the low dimensional space says there are no clusters. So this is what we can do with these perceptual metrics. We can say there's a mismatch. And then of course I need to do something about resolving that mismatch. Okay, so the second part was really like, you know, the one good algorithm that just successfully solves a hard problem. That's the holy grail. That's fantastic. But like, often it's about the trust, right? We need to know, is that algorithm actually solving the problem? And do I trust that solution? And that's when visualization and all these things that we're doing here come into play, right? It's not just pressing the button and here's a perfect solution. And I think this is one of the general challenges in explainable AI at the moment that we're seeing, right? You know, the tools work really, really good, but we don't, at least not always understand why they're working good. And our job as visualization people, and I would argue as researchers and scientists in general, is to better understand. I'm not sure if I correctly interpreted your question, Helvig, but if not, just like, you know, ping me on Discord again.
All right, we have more questions. There's another question by Shiva Agarwal about limitations. What are the limitations of using measures that evaluate how good a visualization is? In what scenarios we should not use them?
No limitations. Everything is perfect. No,
of course.
No, this is of course not the honest answer. Of course, this is a limited approach. So what we can do, what we found is it works really well if we try to model human low-level perception. And I mean the term low-level really in the computer science way. If I talk to like colleagues from psychology, they always laugh at me because for them, we're just doing high-level perception, high-level tasks. But it's really class separability, a correlation. I know Ron Rancic has done fantastic work on, like, you know, modeling the perception of correlation. Our impression is that, like, for those, our modeling approaches work well. But then there's like these entire limitations that you have from, like, you know, perception is not just everything that you need for a good visualization. It's a part. The harder and more tricky part is cognition, so, and sense making. And something like that, modeling that in a way with like, you know, I propose today is really, really hard. At least, like, you know, I don't foresee for the next like 5 or 10 years how we can solve that in a holistic way, like to create these models. I think, like, you know, there we still need to go back to qualitative research methods and, like, you know, working together with people trying to understand what works well. But I think, like, and I provocatively said, like, you know, this approach can automatize visualization design, which I think it cannot, but it can give like guiding tools, like things like the show me feature in Tableau, things like that. You can use these perception metrics and you can ping the designer and say, oh, here's something interesting. Or you can create tools saying like, oh, watch out. So like you created this visualization, but it might not actually perception represent what you want to represent. I think we can have guiding tools, but there's, of course, there's like huge limitations in terms of, like, you know, going to the cognitive level. Did that answer your question? I did. Okay. I think I asked you.
Okay.
Working.
All right. I think so, yes. There are more questions. Another question, a short one, Edo Freeman. By the way, I only read out the question, not all the positive comments, because we are running out of time and there's not enough time for this. Is the Vis4ML tool on GitHub?
No.
That was short answer, short question.
No. It's not on GitHub, but we have a web page where we hosted that. I will put the link here. I'm talking while looking. Just Google Vis4ML. This was the Vis coder. So if you just Google that, I'm doing it myself, you will find the web page of my PhD student, and I'm just posting that here. If it works, yes. And there you go. And there is also the demo. If you need the code, just ping us. I'm not sure if he has the code online as well.
Okay. Further question, what is your position about scalability in dimension reduction methods? How do you deal with this? Scalability.
So that's why I briefly brought up this idea of progressive progressiveness and progressive visual analytics, progressive visualization. I think that's a huge deal if we come to these like machine learning models. If you like use a TSNE on a data set or like a PCA on a data set with like, you know, just 100,000 points, you run into problems. So there's people out there. I know Jean-Daniel Fiquet is working into that direction, and many others that are creating progressive versions of existing dimensionality reduction techniques that make them more scalable. It's a huge problem. Subsampling is as tricky depending on the tasks that you have. So subsampling meaning, just like, you know, take a sample of 10,000 of like your trillion data points. Because like, depending on the task, you might, for instance, miss the important outlier or something like that. It really depends on the task. And so there's methods. It's hugely important. I think for our tools, we're really focusing on these interactive, like, you know, ensemble tools. We usually like, you know, use smaller data sets because just like, you know, we're creating ensembles of models. And if we do that for like large data sets, we're running into problems. This is, by the way, something that we have done in this other ABI paper that is presented in parallel, like, you know, where a model run takes like, I think for them, it took a week. And then like, yeah, of course, you can't like create like, you know, hundreds or even thousands of models. That's obvious, but like, you know, here we can use what we call like, you know, steering methods. So like you can look at ongoing things while the model training is running and then maybe change things and then come back to that process.
Okay, there's one more question by Thomas Schulz.
Mm-hmm.
I'm curious why you focus on the centroid-based measure from Mike Zipp's work. What's your opinion on the entropy-based distribution consistency measure from the same paper? To me, to Thomas, it seems more flexible and more widely applicable in practice.
Yes, thank you very much for the question. So the reason why I focused on the centroid-based measure is twofold. So number one is time. I was given 30 minutes, so I needed to cut out something. So in this Eurovis 2012 paper, we evaluated two metrics, and those were actually the centroid-based metric and the entropy-based metric, both from Mike Zipp's papers. There's also other ones. So why I use that in the talk, one, it's easy to understand and to explain to people. I think like the other one is also not that hard to understand. You have like some boxes you go over, you measure the entropy and you sum that value up. But it was really, we also tested the entropy measure in our study in the 2015 Eurovis paper. And the centroid measure actually came out as the best one currently, modeling the human perception of class separability, with the caveat that we only used like simple and very clear-cut cases. And in other cases, I agree in this qualitative study that the entropy metric worked better, but it also has problems.
Right. I think we are through all the questions and we are perfectly in time. So this is a perfect moment to finish everything. Thanks a lot, Michael, for the very impressive talk and all answering the question. Before we close the session, let me just draw your attention that VMV is going to continue. There's another paper session, and there is the keynote number 3, Humans Against Virus by Hans Christian Hege today at 2 o'clock, which sounds very promising and interesting. And I definitely recommend you to go there. With this, thanks a lot for all the speakers, for their presentations and answering the questions. And with this, let's close this session. Thanks a lot.